Hello YouTube, welcome back to Pre-Calculus, Chapter 12, Section 4, What is Proof by Induction? Okay, so we talked about the Peano postulates today. What does that mean? Well, let's say I want to prove this. Let's say I want sigma, k equals 1 to big N. Big N is some big integer, whatever it is. I'm doing 2k plus 1. What does that mean? All right. Well, if we plug in 1, we get 3. If we plug in 2, we get 5. If we plug in 3, we get 7. And this is sigma notation, so it's a series, we're adding them up. And we're doing a finite series. We're going to end up with, what if we plug in, what was the last term you plugged in? Let's say you plugged in n, and you get 2n plus 1. Now, what kind of series is this? Is this arithmetic, geometric, or neither? It's arithmetic. The common difference is 2. All right. So that means to add them all up, you take the first one and the last one, average them, and multiply by how many? Now notice we counted from 1 to n, like 1 to 30. That would be 30 things, so n. So what we're doing is we're going to try and prove the pattern that we discovered last week, that you average the first and last and multiply by how many to get the sum, no matter how many terms you're doing, if it's finite. We didn't prove that, we just sort of discovered the pattern. Let's prove it now. And we're going to use what's called Peano's postulates, okay? The first postulate, the first step is show that it's good for some integer n. Let's say n equals 1. In other words, you only have one number in your series, 3, and you add them all up. What do you get? 3. Is that the same thing as if you plugged it into your summation, this thing, where n is the number of terms, in other words, n is 1. So is it true that 3 plus 2 times 1 plus 1 over 2 times 1, is that 3? Well, let's see. 2 times 1 is 2, plus 1 is 3, plus 3 is 6, over 2 is 3, times 1 is 3. Check. All right, that's the first step, or the first postulate of Peano's postulates, of proof, which means proving by induction. Now, the second step, you can choose any n to start. N equals 1 is fine, right? But you want consecutive integers now. So what's the next one? So now you're stuck. In the second postulate, you got to use the next consecutive integer to, in this case, to 1 is 2. So what does that mean? We're adding up the first 2 terms. So we should get 8. All right. Is that what we get when we plug into here? N is 2 terms. All right. Let's see. 3 plus 2 times 2 plus 1 over 2, the average of the first and last, times how many? Well, now you see that the 2 on the bottom and the 2 on the outside, that cancels. And 2 times 2 is 4 plus 1 is 5 plus 3 is 8. Check. Yes. Okay, so the first 2 steps are easy. The first 2 steps are arithmetic. The first two of Peano's postulates for inductive proof. This is called Peano's postulates, or proof by induction. Okay? So there's 2 more steps. Now, the last 2 steps are a little bit more tricky. They're algebraic, but hey, what's a little algebra among friends? Shouldn't be too bad. This is what he said. Okay, assume that this is true for some n, because we just proved it was true for 1 and 2. So assume that's true for some n. Can you show that it's true for n plus 1, one more term? If you can do that, then you get a cascade effect. It's good for 1 and 2, we said, right? Then it's good for n and n plus 1, so it's got to be good for 2 and 3, and 3 and 4, and 4 and 5, and 5 and 6, and any n you want. So you've proven that it works for any n you want, as long as n is finite. All right, so let's do that. So the next step is assume it's good to up to some value of n. In other words, what did we say? 3 plus 5 plus 7 plus all the way up to 2n plus 1 equals, well, can we simplify this a little bit? Whoopsie. What did we have? What is, let's see, 2n plus 1 plus 3 is 2n plus 4. 2n plus 4 over 2 reduces to n plus 2, right? Okay, so I'm going to write it that way. Just make it simple. This is the same thing as n plus 2 times n, isn't it? Because we got 2n plus 4 over 2 times n, but that the 2's, you factor out a 2, GCF of 2 in the numerator, divides with the 2 in the denominator, you're left with n plus 2. So I'll write it a little simpler. Let's write it that way. It's n plus 2 times n. All right, so here's the last step. Assume that to prove that it's good up to n plus 1. So what does that mean? Well, we plugged in 1 to get 3. We plugged in 2 to get 5. We plugged in 3 to get 7. All the way up to, we plugged in n to get 2n plus 1. So what if we plug in n plus 1? plug in n plus 1 into there. So plus 2 times n plus 1 plus 1. Okay, so now, over here, the n means how many terms? Well, we're counting from 1 to n plus 1 now, right? So wherever we see n, write in n plus 1. Okay, so the thing is this. The assumption is true, because we proved it, at least for some n, arithmetically. Can we show that the line above is true also, so then it's true for all n, a finite number of n's? And the easy way to do this right now is to subtract, because look what happens if we subtract the bottom equation from the top equation. The 3's cancel, the 5's cancel, everything up to 2n plus 1 cancels. All that's left on the left-hand side of the equal sign is 2 times n plus 1 plus 1. Okay, so do the same thing on the other side. Subtract those two. By the way, what is n plus 1 plus 2? Isn't that n plus 3? So I'm going to say n plus 3 times, whoops, I wrote that wrong. Remember, this is how many terms we're adding up? And so is this. So I should have an n plus 1 over here. Sorry. So I'm going to do n plus 3 times n plus 1 minus n plus 2 times n. All right, now this is like an identity proof or a check. You want to simplify both sides separately. Don't cross the equal sign. You already did all your algebra you have to do. Just do a check and make sure that both sides simplify to the same thing. If you get the same thing on both sides, that's clearly true. So all the equations prior to that is true. In other words, if I subtract the assume n line from this assume n plus 1 line, and the answer I get is also true, all three equations were true, and we proved everything. All right, let's simplify. What is 2 times n plus 1? 2n plus 2 plus another one, 3. Now, can you simplify the left-hand side anymore? No, not really. So the idea is to make sure you can simplify the right-hand side so it looks exactly the same. Alrighty, so let's do that. FOIL these first two binomials. First times first, outer times outer, inner times inner, last times last. Minus, well, distribute the n squared plus 2n. So what do you got here, really? You got n squared plus 4n plus 3 minus n squared plus 2n. And is that the same? Not yet. I'm going to be exactly the same. All right, subtract n squared minus n squared. They cancel. Subtract 4n minus 2n. You get 2n. And this is plus 3 over here. Is that what you wanted? And it's like a check. And this is when you do your QED dance. You've proven this beyond a shadow of a doubt. QED is Latin for quod est demonstratum. That's what they used to write when they published original work like this. And they proved stuff. Everything was published in Latin years ago, hundreds of years ago. And they write quod est demonstratum. That which is demonstrated or proven beyond a shadow of a doubt for now and for always. You don't have to prove it again. Everyone can use this now. This new result, it's amazing. So what did we prove? That 3 plus 5 plus 7 all the way up to 2n plus 1 is, in fact, n plus 2 times n. Okay? And there you go. All right, so that's an example of Peano's postulates proof. And this works if whether you're having arithmetic sequences or geometric sequences. Sometimes you get some weird expressions that maybe instead of subtracting the n line from the n plus 1 line, you're going to divide and get something out of that. That works too. All right, so there you go. There's an example of what you want to do on the homework. Homework is page 843 multiplied by 5. And that's it for today. Bye-bye, YouTube. Have fun. Hope that was helpful.